Hi, I'm Zachary Segall. I am a Math, CS, and Policy Studies major from the class of 2018, and I was the software developer for the Grinnell College Immersive Experiences Lab during the 2017-2018 school year. And I'm here to give this talk to sort of explain some of the things we learned during this school year and, try to provide a little bit of a roadmap for future software developers with GCL. So they don't have to repeat as many of the mistakes that I made. All right, so I want to start by talking a little bit about the background behind the project. For people who haven't used VR before, there's just a little bit of terminology and some technology that you should know about for this team. So in terms of VR technology, there are, at the time of this recording, two really major companies producing VR technology. There is Oculus and HTC. The Oculus's headset is called the Rift, and it is the bottom 5 pieces of technology on the screen. And the Vive has the HTC has the Vive, and it's the top 5. These are the commercially available gaming headsets for VR. Both of them actually just released new versions of these in April-May 2018. And a headset typically consists of the headset itself. Those are in the middle. That's what you put on your head, and has cameras so that it shows you the 3D VR environment. Then you also have controllers, which are adjacent to the headsets. Those have sort of evolved from video game controllers and use a lot of the same keypad and naming conventions. And then you have sensors, which are on the sides and the tops. Those track the headsets and the controllers, and are used to get the position of the user so that they can be put in the proper place in the gamer experience. So once you have one of these, you need to get games and experience from somewhere. Both Vive and Rift have stores, and these work just on the computer and in VR. You can put it on a headset and sort of see all of the options that there are. And there's also another third-party distributor called Steam. Steam is a game distribution company, and they have, since their inception, they've also branched into VR these days, and they are also working on some of their own software support for cross-platform VR technology, which we'll be talking a little about later. But basically, these are the stores, the distribution centers through which people usually find VR experiences. So now I want to talk a little bit more about what a VR experience looks like, and I'll do that by playing part of a video we had that we created this year. So just a little bit of context: this is a part of a recreation, very much in progress, of a sugar plantation from the 1800s. We had a bunch of great blueprints for this site and wanted to use it to teach about slavery and history. So I will start that now. All right, so there are a lot of things going on here, and I wanted to unpack a little bit about all the different components that go into a VR experience and what we might need to build. So there are a lot of them. There's sound, which we didn't do for this experience. We didn't have anyone to work on that, unfortunately. You've got visuals, as you can see. There's houses and objects. These are the slave cabins, actually. Animations, we didn't get to show that off here, but that's definitely another part of it. Physics, picking up the cube. If you throw those cubes, they'll fall back to the ground like a physical object would. Game logic, sort of what happens how you manage the game state when you put a cube in the fireplace. It has to snap in place and whatnot. Then you have user interface and narrative. So like user interface is clearly like what buttons do you press, how do you interact with the environment, and narrative, we didn't show off too much here clearly. It's generally like what's the premise of the experience and how do you move through it. There's a lot of parts to a VR experience, and I'm going to talk more about them in a moment, but I want to just give a little bit of a background on design and development, because in college we focus mostly on the development side. How do you build things? How do you make programs that accomplish whatever goal you want? And that's mostly all we do in class. You have very clear-cut, clean assignments that you can finish in a week or maybe a few weeks if it's an end of the semester project. You know exactly what you need to make in order for your project to be successful. You just follow the requirements laid out by your professor, and you know what success looks like. In a larger project like this, that's much less clearly defined. We started with some blueprints for the Uncle Sam Plantation, and we knew we wanted to talk about slavery and sugar plantations and educate students on that. But that's all we started with. We did not have many clear requirements to go off of. It wasn't exactly clear what we were going to build. So somehow we have to turn that initial starting material, those problems, and take that and turn that into something that we can very specifically just sit down and build. And that's sort of what design is about. Design is about taking this open problem space and figuring out how you are going to satisfy your constraints and your problems, versus development, which is figuring out, once you know what you want to make, how do you actually make it? How do you get there? So a lot of the presentation will sort of look at jobs and tasks through the lens of either design or development, and I'll get into more of those specifics later, but I wanted to use design and development to sort of frame how we build each part of the VR experience. So, in this past year, we had different team members working on different aspects of the game. We had, me, a software developer, we had a 3D artist, and we had a subject matter expert. And in terms of, like things like visuals and animations, the design was, up to the artist and the subject matter expert, who sort of had different roles. The subject matter expert would find, the historical background on what we were making, and the 3D artist would figure out, what it should look like. But then the person to actually sit down and build that in experience, that's going to be the artist. And for things like physics, we didn't really design that. Physics are just supposed to behave like they will in the real world. And development, we actually let the Unity game engine handle most of it, and all of it in this project, and probably that'll be the case in future projects. But then things like the game logic and the user interface and what narrative we want get figured out by the team, and then, the game logic and the user interface do get implemented by the software developer. So those are sort of the areas I'm going to be focusing on, because this video is supposed for briefing software developers. So that's really what I'm going to hone in on and look at what developing game logic and user interface and some other details look like for software developers. So I have 5 general software developer responsibilities. I took what I did this year and tried to condense it and summarize it in 5 different responsibilities. Again, I broke it up into development versus design, and I'm going to start on the development side. So the first is understanding Unity. Unity is a very complicated but powerful tool, and one of the major roles of the software developer is to understand how it works so you can sort of provide support in building the experience to the team. The next will be assembling the UI and interaction system. Clearly, if you're going to have a functioning experience, people have to be able to interface with it. So building the UI is a critical part of the software developer's responsibilities. And then clearly implementing the game logic, you need to have some sort of flow through the experience and know what's going to happen. This is another big one. Then on the design side, there will be a lot of contributions to experience design. You'll help with the brainstorming and deciding what the experience is going to be about. And there will also be prototype testing, because you can't know what your experience is going to be like without testing, and testing is a critical part of sort of the process of refining how the experience is and improving it. So I'm going to just go through these and provide more details about them and the lessons we learned along the way. So for development, let's start with understanding Unity. So I know that for all Grinnell students, most CS students in Grinnell have taken 161, which is our intro, our class that introduces C, and in 161 we use Emacs, the text editor, and I don't know how everyone else got through 161, but the way I did it was just sort of learning the bare minimum I needed to get by with Emacs. I learned how to save files, and I learned how to copy and paste and quit, and that was pretty much it. And I sort of ignored the rest of the functionality of Emacs. Now, there are people out there who know Emacs inside and out. They know a lot of the macros and the shortcuts and the hotkeys, and they know how to make it work for them, and they can code much more quickly and effectively in Emacs. So I tend to view Unity as a similar way. You can either learn the bare minimum you need to know to get by, or you can really learn about all of the quirks and idiosyncrasies and ins and outs of Unity and then be a much more effective developer. I learned the just enough to get by route again, and that was not the best choice. I really wasn't able to take advantage of the full potential that Unity has because of it, and that's one of the reasons why we're encouraging developers now to do a Unity course before they start working, is so they can get a chance to master Unity on their own before the project. Because Unity does have a lot of out-of-the-box functionality, and if you know what Unity is capable of, you'll spend a lot less time trying to figure things out and be able to build, effective, concise code in these projects. And the more fluent you are, the better you'll develop with it. And again, another one of the lessons we learned was that trying to learn Unity and work on the project, which is what we did this year, didn't work so well. Or learning how to work with VR. Steam VR is Steam's cross-platform interface for VR. And that, again, didn't work out well. We were split too many directions, which is, like I said, one of the reasons why we're encouraging developers to get familiar with Unity before they start working on the projects for G Seal. So with that in mind about Unity, I want to move on to UI and VR interaction systems. So generally, the idea for an interaction system in UI is sort of build up from the hardware. You need a hardware to you need hardware to you do anything with VR, but once you have that, you need to somehow get input and interaction from hardware and turn that into some sort of user experience. So on top of hardware, you have a hardware-software interface, which translates inputs from the hardware into software events and inputs. And then on top of that, we have what I've been calling an interaction system, which sort of determines how the player moves throughout the thing. Teleportation is how we did it. You might want to look into other ways. Object interactions, picking up, placing, using, throwing objects, because that all has to be programmed in somewhere. And traditional UI, we also have buttons and menus within the experience. But the interaction system is basically just what translates the inputs we get from the hardware from the hardware-software interface into commands, so that you can navigate, interact with objects, and press buttons. And then on top of that, we have the actual specific game objects and how those work and how you interaction with those create parts of the experience. So building an interaction system is complicated, and there are a couple ways to get the code to do that. You can either use an external library, API, or toolkit, or build our own. At the beginning of this year, we started out with VRTK, which is a virtual reality toolkit. It was this project by this guy who wanted to build sort of a toolkit, a basic set of functionality that people could use to develop VR experiences. So we used this for the first semester, and then at the end of that semester, the developer announced that he wouldn't be supporting VRTK anymore. So then we had to choose whether or not we wanted to use this toolkit that wouldn't be getting support in the future, or if we wanted to switch to something different. So we ultimately decided to switch to something different, and we looked at two other toolkits. We looked at Steam VR, which is Steam's VR, again, toolkit and sort of cross-platform interface that works with both Rift and Vive. And also we looked at Newton VR, which is made by Tomorrow Today Labs, and their toolkit sort of focuses on getting good realistic physics. So after, comparing these two and trying them out, we decided to try to use Steam VRs. And we started working with that, and then we got to a point in the experience we were building where Steam VR wasn't working the way we wanted it to, and we weren't sure how to get it to do that. So at that point, we just decided to build our own toolkit. And we did this starting from some tutorials we found online, and decided to just, expand on that basic functionality. But this is a major thing you'll have to be thinking about when developing for GCL is, where do you want to get your interactivity from? What code are you going to use to support that functionality? And you will have to keep asking these tools of what toolkit do you want to use, because VRTK is now being supported by Oculus, so you might have to consider going back to that. Of course, this will all be outdated in a year, so we'll see where everything ends up. So third, we have the game logic or control flow, and I'm going to explain it with XKCD because, hopefully that makes it more entertaining. So control flow is just sort of about how do you manage the state of the experience, the state of the game, and how do player actions influence the state. For example, this past semester we worked on a project with a German language learning game where you have to pick up bottles and go recycle bottles around this fictitious German town. And, in this experience, we need to know, how many bottles of each color there are, how many bottles the user's collected, because once the user collects all the bottles, we should end the experience and, tell them that they won or they completed it and, give them feedback. So we need a way of tracking the state and a way of managing all of this information. So basically, control flow is telling us, what happens when and why. And in order to do this, the traditional way in Unity is to use a game manager. And a game manager is sort of this singleton object that just stores all of the information about the game, and it's connected up to other objects in Unity, and they pass information back and forth. And when you get to a certain threshold, it'll trigger some function and call it in an object. But this is kind of bad design for anyone with experience in computer science development background. Code should be modular. Code should be broken up into small pieces, and each piece should only do one thing. And the game manager is clearly doing way more than just one task. And especially as experiences get bigger, game managers get clunkier, and you're storing a lot of information that has nothing to do with itself, or a lot of unrelated information, where the only connection between the information is that information is sort of global and needs to be known by a lot of different game objects. So we looked for a better solution, and we found doing control flow with scriptable objects. Now, scriptable objects are basically just files. Game objects can write to scriptable objects, and other game objects can read from them. So you sort of have these individual files that represent different pieces of information that you can write to and read from without touching any of the others. So that's much more modular, it's much more broken up. And another nice thing about scriptable objects is that since they're files, they persist between play sessions. So you really only have to clear them if you want to reset things. And they generally help with memory persistence. There are some other advantages to them. We got most of our information from a Unite talk which is the yearly conference for Unity development. I will have links for those videos, and we'll be attaching them to a resource sheet at the bottom of this video. So that's another major thing you're going to have to think about, is how are you going to implement control flow. I would personally recommend scriptable objects, but you should look into both options and make that decision. All right, so let's talk about the design half now. Now, I'm going to be assuming very little background on design because most of what we do at Grinnell doesn't really get as much into design. Like I mentioned, all of our examples are sort of predetermined, and there's not, you very rarely have to define what it means to be successful in your assignments. So designing an experience, at its heart, I'm just going to go over the basics. At its heart, just sort of composes a cycle of activities that lets us go from, an undefined product to a, functional working product. So everything starts with constraints. Like I said, for our Uncle Sam Plantation project, we started with some blueprints and a desire to talk or teach about history. These can be very open-ended, and you can have lots of different constraints. This will probably be something that gets worked out with whatever subject matter experts you're working with and whatever professors are sponsoring the projects. After you have your constraints, you brainstorm, just create a bunch of ideas, and then pick from those the best to try to move forward with. And then prototype, trying to create as simple as you can a version of the product so you can test it and then get feedback, and then it loops back to maybe brainstorm or prototyping once you have data from tests. So I'm going to focus on brainstorming for now because constraints are covered by whatever subject you're working with. Prototyping is just the development things we talked about, and testing I will get to in the next slide. So again, brainstorming, I want to cover the basics because it's not really covered in the Grinnell CS curriculum. So basically, the idea behind brainstorming is that it's easier to recognize an idea that fits your constraints than to take a bunch of constraints and specifically design an idea that satisfies them. So brainstorming is sort of based on some of the notions that you need to, there will be a lot of bad ideas and a few good ideas, and you need to get through the bad ideas to find the good ideas. So brainstorming works a lot like improv, where they have this rule called yes and. You don't say no to anyone in improv, you say yes, and then you build off of what they're thinking. So brainstorming needs to be a similarly collaborative environment where people feel comfortable throwing out bad ideas, and you don't shoot anyone down, and importantly, don't start evaluating. In computer science, it's easy to assess our programs and make judgments about how good or how elegant or how functional our code is, but that's not the point in brainstorming. We really just want to get as many ideas as possible, and then from that will usually emerge some solid ideas and ideas that try to incorporate the best of all worlds. Another way in which brainstorming sort of differs from computer science as we might be used to it is that we throw out the majority of ideas that we come up in brainstorming. Case in point, this is a whiteboard of the brainstorming we did at the beginning of this semester to sort of find a direction for our Uncle Sam experience, and we threw out all but 3 of these ideas, which just goes to show that you won't be keeping most things, and you have to be comfortable coming up with ideas and then quickly letting them go. So if you want to learn more about design, I have a couple recommendations for resources. There is a YouTube channel called Extra Credits, which does videos on games, the state of games, and game design. And not all of their videos are on topic, but they do have a lot of great information on game design, which is very easily transferable over to the kind of experience design that we're doing. And then there's also The Design of Everyday Things by Don Norman. It's a classic for learning about design. Now that we've talked a little bit about design, let's talk about testing. Again, testing is one of these things that isn't covered super in-depth in the Grinnell CS curriculum, but it's a critical part of the product development process. So very briefly, I'm going to talk through what a test looks like and then give a little bit of advice on how to run tests. So, just last week we ran our first tests for one of the German learning experience we've been working on. And basically all we did is we brought people into the lab. I sort of explained what the experience was about, and then I put the headset on them, or helped them put on the headset, gave them the controllers, launched the experience, and just sort of let them figure their way through it. Now, while this was going on, I did take notes on how they were doing, and after they finished, we took the headset off, and I debriefed. I asked them about how the experience was and asked if they have any feedback. So that's sort of what a test often looks like. And the idea behind testing is this idea of fail faster, which basically just means that, or is predicated on the idea that you don't know what's wrong with your experience until you see it in action. You can theorize about, what people might do all day long, but there's no substitute for actually getting people to sit down, or in our case, stand up and try the VR experience. And when people do, you'll be able to find out where they get stuck and what they have problems with, and then make a more effective experience as a result. So in order to make a good test, you want it to mimic natural use as much as possible. You want an authentic experience so that you can see where people get stuck. And one of the most challenging things to creating this authentic experience is to not correct people. It can be really hard to just let people make mistakes and let people struggle with how you put your experience together, especially when you know all of the ins and outs and you know exactly what they should be doing. And it can be very tempting to correct people and say, just do this one thing and then it'll work fine. But if you do that, you're depriving yourself of very important data, because you need to know where people have trouble figuring out your experience so you can make those parts of it smoother. And if you tell people up front or very quickly how to use things, you won't get that data, and that's not how people will be using it once the experience goes out into the real world. So you do want to take notes, and that connects right back to looking at where people have trouble with the experience. You need to write down where that's happening, and so that you have a record of what the problems are. And related to taking notes, you want to make sure you get context for the user. In the case of VR, what I mean by this is it's important to know whether or not people have used VR before and how much experience with games people have. We want to make our experiences as accessible as possible, and someone who has their own personal VR headset is going to have a very different experience from someone who's never played video games or who doesn't play video games much and just isn't familiar with the medium. So making sure that you know where people are in terms of experience level and background is important so that you can make sure you properly interpret, the difficulties they're having and how they interact with the experience. And after, when you're getting feedback about the experience, you really want to avoid leading questions. Now, for those of you who aren't familiar with this term, leading questions are basically just questions that sort of suggest an answer to people. Like if you ask, do you like my game? Then people are probably going to be more inclined to say yes. People want to be friendly and supportive, so they might give you the answer they think you want to hear rather than their true opinions. And you need their real opinions, because there's no way to improve an experience if you don't have, good feedback on what people thought of it. And finally, you generally want to take video and recording whenever possible. Make sure that people are comfortable with you recording them, because this is just another great source of data. Taking notes can't capture everything, and when you're watching video and watching through the camera, especially for VR, of what someone looks at, you can get a lot of great data. And having all of these notes and these recordings is super important for talking to a team who wasn't there at a test and who didn't see how someone used your VR experience. So having these materials lets you, make a case for why something works or something doesn't work, and what needs to happen to change the experience, to take that into account. All right, so we're almost done. There was a lot of material on, the 5 core responsibilities that I think a software developer for GCL has. I'm going to end with some odds and ends advice on things we picked up this year. So maybe the biggest surprise for me this year was that I was not spending the majority of my time coding, and you probably won't be either. Again, this is very different from class where, if you spend 3 hours working on a project, you might write 300 lines of code. There's a very clear time in to code out relationship a lot of the time. But that's not true for GCL. So you might ask, what are you going to be doing instead? And there are a few things. The first is just figuring out Unity and debugging. As I mentioned at the beginning, Unity is a very powerful tool with a lot of built-in functionality. So you might not need to write much code, but might need to spend a lot of time learning about what code you need to write. There are definitely times when I've spent 3 hours looking up code and wound up writing 2 lines of code. So it's a very different experience than class. And the 2 lines worked perfectly. They did exactly what I wanted to, but I spent a lot of time getting there. Similarly, you'll be spending a lot of time researching not just Unity, but also VRTK, Steam VR, like these interaction system toolkits, and figuring out when to use different things. So that, again, can take a lot of time and not result in very much code. You can also will spend a lot of time discussing content and design. That's sort of a whole team activity. And then, again, involves no code. That's just meeting and talking and figuring things out. And then finally, you'll do a lot of testing prototypes and revising, the process which I just described. And that involves no code, but will inform what code you write. So there is a bunch of activities that involve, minimal code writing, but are very important to the process, and you do need a background in programming to really, take these activities and turn them into code and turn all of the information you get into coded projects. Second, work in longer chunks. At the beginning, in the first semester on this project, I tried to work an hour a day, and that was a bad idea because I ended up fighting with Unity for like a half hour, and then I only had a half hour to code, and I couldn't get much done in that time. I just couldn't ramp up my productivity well enough. So this semester I've been working for 2 or 3 hour chunks, and I've been able to get a lot more done in that time. So I would advise working in longer chunks if you can. Next, be prepared for cross-discipline communication speed bumps, especially if you're working with fields who don't have much experience with computer science or coding. You will have very different ways of approaching problems, and you need to be ready for this and just prepared to understand a different way of approaching problems and be prepared to explain how you approach problems and all the sort of assumptions and things you take for granted. And finally, test early, test often. We did not run many tests this year, and I feel like we were missing on a vital part of the development process. So I would really stress trying to make sure you test, at least monthly, testing more often, and just getting data and making sure that your experience actually works out the way you want it to. You don't even need a full functioning product to do tests. You can just mock things up in pencil and paper if you need to and bring people in and test that. But just make sure you're testing. All right, so that is generally what we learned from this year working in GCL, and I hope that this has been helpful for sort of giving a context to what a software developer at GCL does and maybe giving you an idea of what you need to think about for the future. good luck, and I look forward to seeing what everyone makes.